Welcome. Today we will discuss variable frequency induction motor drive operating from variable frequency source. So we are considering induction motor fed from inverters cycloconverters or matrix converter. So the principle is frequency control. As you know, the synchronous speed of the induction motor omega s is given by 4 pi f by p radian per second, where p is the number of poles and f is the supply frequency. This is the synchronous speed, and motor speed is omega m, that is 1 minus s times omega s, where s is the slip. Slip can be varied only in a limited range, and because synchronous speed is directly proportional to frequency, by varying the frequency, synchronous speed can be varied over a wide range, and hence motor speed can be varied over a wide range. Motor speed can be varied from 0 speed to very high speed. Over a wide range from 0 speed rest condition to very high speed above the rated speed. The maximum speed is decided by the mechanical design constraint and construction of motor. So frequency control gives a wide range of speed control, so very well highly preferred. So open loop speed control through direct change of frequency has certain constraints or restrictions, as I am going to mention now. In induction motor, the stator induced EMF per phase denoted as E1 is root 2 pi, that is 4.44 frequency f phi into T phase 1 into KW1, where phi is the flux per pole, T phase 1 is the stator turns per phase, and KW1 equal to winding factor of the stator winding that is Kp1 into Kd1, that is Kp1 is the pitch factor and Kd1 is the distribution factor. So stator applied voltage per phase which is V1 is given in the phasor form as V1 phasor is E1 phasor plus I1 Z1 phasor. Z1 equals to R1 plus JX1 is the stator impedance per phase I1 is the stator current per phase. So stator impedance drop which is I1 Z1 at full load is less than 10% of the rated voltage. So, if stator impedance drop is neglected, then V1 is nearly equal to E1, approximately equal. So, and E1 is 4.44 F phi T phase 1 into KW1, nearly equal to. So, if applied voltage V1 is constant, the product F into phi is also constant. So, as for a constant V1, F phi product is constant, keeping V1 constant, if the frequency F is reduced, flux phi increases. If F is increased, then flux phi reduces. So, with this we will discuss the constraints on the V-wave control. So, now with this consideration, mathematical discussion analysis, we will discuss. So, if the supply voltage V is kept constant and frequency is reduced, then flux per pole phi increases. And as you see, as motors are designed to operate at the knee point of the magnetization characteristics to make the full use of the magnetic material, increase in flux saturates the core, because BH curve is nonlinear. All of you know the BH curve of the magnetic core of the machines, and the normal operating point is knee point of the magnetization characteristics just before the saturation, So, when the frequency is reduced keeping voltage constant, flux increases, and as flux increases, the flux density also increases. So, the machine operates into saturation region. So, the core gets saturated, magnetic core gets saturated, and under this saturation due to the saturation, magnetizing current increases. Obviously, with as saturation it draws more current, magnetizing current increases, the line current increases, also the line current gets distorted, because magnetizing current increases, the line current increases, and line current gets distorted because of the nonlinear nature of the BH curve. It becomes non-sinusoidal, the line current becomes non-sinusoidal. Core loss increases, stator copper loss increases, because stator current also increases, and high pitch acoustic noise is produced. So, saturation of core flux is undesirable. Variable frequency control below the rated frequency is performed at the rated air gap flux by controlling the terminal voltage with frequency, so that the V by F ratio is constant at the rated value. This is constant V by F control. So, for variable frequency, because of this demerits of the saturation, it is always preferred to operate the motor at the constant rated air gap flux. So, for the speed control below the rated speed, when the frequency is reduced below the rated frequency, air gap flux is maintained constant at the rated value, and this is done by controlling the voltage, so that the V by F ratio is constant. If V by F ratio is constant, then phi is constant, and that phi constant is rated flux. So, this is constant V by F control. As the core flux is constant for this range of operation below the rated speed, core flux is constant at the rated value, the maximum torque is also the same at different frequencies, except at low speeds or low frequencies, because maximum torque depends upon the flux per pole, and the flux per pole is maintained constant at the rated value at different frequencies. So, the maximum torque is also constant at different frequencies, but it reduces at low speeds or low frequencies, that we will discuss. The machine, because the flux is constant and maximum torque is constant, machine speed characteristics for the region of operation between 0 to sleep range from 0 to SM sleep SM, or say synchronous speed. At sleep is 0 at synchronous speed, and at maximum torque sleep is SM. So, within these 2 points, that means synchronous speed and maximum torque point, 0 sleep between 0 and SM, the torque speed characteristics are approximately parallel curves. So, motor operates in constant torque mode, because maximum torque is constant. So, motor operates in constant torque mode. At low frequencies or low speeds, applied voltage is less proportionally for constant V by F control. At low frequencies, applied voltage is also proportionally less. Stator reactance is also proportionally less, because reactance is proportional to frequency, reactance is proportionally less, but stator resistance drop is almost constant and a major part of the applied voltage, which is stator impedance drop decides the induced EMF per phase, because stator applied voltage per phase minus stator impedance drop is the induced EMF per phase in the stator winding. And impedance drop has 2 parts, resistance drop and reactance drop. At low frequencies, voltage is proportionally less, reactance is proportionally less, but resistance is constant, almost constant. So, stator resistance, because applied voltage is very small, the stator resistance drop is a major part of the applied voltage. At low values of frequency and speed, because of the because stator resistance drop is a considerable part of the applied voltage, the back EMF reduces more than the proportional value, and hence the core flux and maximum torque reduced from the rated value. When it is required that the same maximum torque is retained at low speeds, V by F ratio is increased at low frequencies. So, because flux reduces because of stator resistance drop, to make the flux maintain the flux at the rated value, the V by F ratio is increased more at the from the V by F ratio is increased more at the low frequencies above the value corresponding to rated condition. And frequency control above the rated frequency. So, when V reaches rated value at rated frequency, voltage is the rated voltage, and if frequency, if the speed is to be increased above the rated speed, frequency has to be increased above the rated frequency. but voltage cannot be increased further with frequency because of limitations imposed by the stator winding insulation. V by F ratio requires that if the frequency is high, the voltage should be high. At rated voltage frequency, voltage is rated. At speeds, for speeds higher than the rated speed, frequency has to be higher than the rated frequency, but voltage cannot be increased above the rated voltage due to limitations imposed by the stator winding insulation. Insulation failure can occur. So, there will be short circuit and winding will be damaged. So, stator voltage cannot be more than the rated voltage. So, above base speed, frequency is changed with voltage maintained constant at the rated value. So, voltage is kept constant at the rated value, only frequency is increased to increase the speed. So, because voltage is constant, product F phi is constant and frequency is increased to increase the speed, flux reduces. So, core flux decreases in inverse proportion to speed or inverse proportion to the frequency, and because flux decreases, the maximum torque also decreases, because maximum torque depends upon the flux per pole. As the flux per pole decreases in inverse proportion to speed, the maximum torque also decreases in inverse proportion to the speed. This technique is suitably used for loads whose demand torque varies inversely to speed in that range, giving constant power mode of operation. Because the flux is inversely proportional to the speed or frequency, and maximum torque is inversely proportional to torque and frequency. So, the torque has to be inversely proportional to the load torque should be inversely proportional to frequency. So, that power is constant, frequency speed is proportional to frequency. So, motor torque should be inversely proportional to the speed. So, it is suitable for a constant power load. So, this range of this operation gives constant power mode of operation. So, the torque speed characteristics are like this. So, torque speed So, this blue line is corresponding to the rated frequency 50 hertz. So, 50 hertz 4 pole machine synchronous speed is 157 rpm. So, this blue one is for the rated frequency of 50 hertz for the 4 pole machine, and as the frequency is reduced, you get the green line, green characteristics, then red characteristics further increased. So, like that. So, you can see the maximum torque is almost constant when the frequency is reduced, except for this graph which is frequency has reduced considerably. So, frequency is low, so maximum torque reduces, and so if the maximum flux is to be maintained constant at the rated value, if the V by F ratio is increased, then the maximum torque can be made equal to the corresponding to the rated frequency. So, these 5 characteristics are for reduced frequency below the rated frequency, and when the frequency is rated increased above the rated frequency, you get yellow one and then black one and then again blue one. These characteristics for speeds above the rated speed and frequency above the rated frequency. So, as you can see, for high speed operation, the maximum torque follows a hyperbolic graph. Maximum torque is inversely proportional to the speed and frequency. So, these are the speed torque characteristics with variable frequency drive obtained from simulation of the motor. So, variable frequency control provides good steady state performance, good running performance and good transient performance because of the following features. First, the speed control and braking are available over a wide speed range from 0 to above the rated speed. So, speed control and braking are available where speed range is very wide. So, it is good performance. During starting, braking and speed control, speed reversal, transients, the operation can be done at the maximum torque with reduced current, giving good dynamic response. So, during transient for the transients of starting, braking and speed reversal, the operation should be done at the maximum torque, because torque is maximum. The operation can be done with reduced current. So, transient response is good, because current is less, copper losses are low. So, efficiency is high and power factor is also high because of the reduced current. Drop in speed from no load to full load is also small. So, these are the advantages of variable frequency control. So, let us discuss the advantages of variable speed induction motor drive, squirrel cage induction motor drive. Squirrel cage induction motors are very rugged, reliable, maintenance free, low cost, has long life compared to, these are the advantages compared to DC motor, and it can be used in volatile environment where fire risk is there, explosive environments and contaminated environment due to absence of commutator. In DC motor, commutator and brush, it requires frequent maintenance, because at the commutator and brush sparking occurs. So, because sparking occurs, it cannot be used in volatile environment where fire risk is there. In explosive environments, it cannot be used, because and in contaminated environments also DC motors cannot be used. But squirrel cage induction motor, because commutator and brush are absent, so it can be used in all these environments, harsh environments. It can be designed for higher speeds, voltage and power ratings. Obviously, squirrel cage induction motors are high, rugged and reliable, and they can be constructed with high speeds, high power voltage and high power ratings. It has lower volume, lower weight and lower inertia compared to DC motor. The only demerit of squirrel cage induction motor compared to DC motor is in speed control. In DC motor, easy speed control over a wide speed range is obtained, but in induction motors or particular squirrel cage induction motor, the speed control is limited in very narrow range. Speed control is obtained, not so easily. Speed control is not so easy. So, speed control is not good as it is in DC motor. So, the advantages of variable frequency squirrel cage motor. Advantages of variable speed squirrel cage motor are that squirrel cage motor. So, the only demerit of DC motor is poor speed control. So, the advantages of variable frequency squirrel cage motor drive outweighs the advantages of DC motor. The cost difference is constantly reducing due to developments in semiconductor technology. The additional cost of squirrel cage induction motor is less, but variable frequency squirrel cage induction variable frequency squirrel cage motor drive, including the power electronic converter one, the cost is more compared to DC motor, but the difference of cost is constantly reducing due to developments in semiconductor technology. So, variable frequency induction motor drives are preferred over DC motor drives for most applications. Applications of variable speed induction motor drive are in mines, tractions, almost many industries, all the industries, underwater applications, underground applications, installations, pumps, fans and blowers, all these applications prefer variable frequency induction motor drive. Okay. Thank you for attention.